Okay, we're going to talk about nuclear chemistry. And one of the reasons why we call it nuclear chemistry is because we're talking about changes that happen within the nucleus of an atom. An atomic bomb, like you see right here in the GIF, is an example of a nuclear reaction because you have changes undergoing in the nucleus of the atom. And so a question I get asked a lot is, why are some things radioactive and give off radiation and other things do not? And so one of the things that makes that happen is, well, anytime you have an unstable nucleus, it's going to be radioactive. We call those radioactivities. And so when it's unstable, it wants to try to get to something that's stable by changing its nucleus somehow. Usually it releases some extra particles. And so unstable nuclei happen when they're just too big. Like you try to cram a bunch of protons and neutrons in such a small little area called the nucleus, they don't want to be there because it's just too dense. And so heavy nuclei, and those would be anything greater than atomic number 83. And so if I grab my periodic table right here, that means bismuth right here, Bi, is the last naturally occurring stable element. So polonium, Po right here, all these that follow after it, and down here are radioactive, okay, because they're just too big. So one way something's unstable is if they're just too big, the nucleus is too big. Another way is when they have too few or too many protons compared to neutrons. So it's all about the proton to neutron ratio. So for example, carbon-12 has a mass of 12, and I know from the periodic table, its atomic number, right? Atomic number is on top. It's a 6, which means it has 6 protons. And then if I do 12 minus 6, that tells me 6 neutrons. So I have a nice even proton to neutron ratio, and that makes carbon-12 very stable. Carbon-14, on the other hand, has a mass of 14. It still has an atomic number of 6, so it still has 6 protons. But now if I do mass number minus protons, 14 minus 6, I get 8. So this one has 8 neutrons, and now that's an unequal proton to neutron ratio. And that's something that would be unstable. And unstable is really just another word for radioactive, okay? When the nucleus is not stable, what it wants to do is eject or emit energy or particles until it becomes stable. This is called radioactive decay. Okay, when it just naturally does it, it just decays. During decay, though, you have to understand the atom does not just disappear. It is becoming a different element because the nucleus itself is changing. And then what's inside the nucleus is kind of what defines what that atom is, okay? Nuclear reactions, when you have something going on inside the nucleus, that releases huge amounts of energy, 1,000,000 times more energy than a regular chemical reaction, okay? So now there's 3 types of particles that they will eject. Some are particles and some are energy. Three forms right down here, okay? The first one we're going to talk about is the alpha particle. Now, we call it alpha, but what it really is, here's the symbol for it right here. And you see that it's really just helium nucleus. Helium has a mass of 4, an atomic number of 2. And it would have a +2 charge as well, although we didn't write that over here on the helium particle. It's made up of 2 protons and 2 neutrons because we can get that from the mass and the atomic number. Helium is relatively harmless. It can be blocked, and that's what makes it harmless, is that it basically can be blocked by paper or skin. So if I had an element sitting next to me that was emitting alpha particles, I wouldn't be that worried, all right, because the particles would just bounce off my skin and it wouldn't get inside me to do any harm. However, if I had an alpha particle in the form of my drink, and I drank some, because sometimes alpha particles actually get in your water supply, and we drink them sometimes without even realizing it. Now it's inside my body, and now it can do harm. It can get into the nucleus of your cells and damage them. So alpha isn't very harmful if you don't ingest it, but the minute it finds its way inside your body, it can be harmful, okay? Now, where you see alpha emitters in an everyday situation is that's exactly what's in your smoke detector. And when the smoke comes by and it's emitting alpha particles, the smoke comes by and it can block it, right? It's easily blocked by smoke as well as paper or skin. And so that's how the smoke detector knows that there's smoke, because the alpha particle has been blocked. All right, the next is a beta particle. What a beta particle is essentially an electron. Here's the symbol for it. And so electrons are basically massless. I mean, they do have a mass, but it's so small we neglect it. So the mass number that goes here is a 0 because it has no mass. And then this number down here, it really is essentially what its charge is. It's a -1, and it's kind of what it does to the nucleus. Minus is 1. Okay, so it's a high-speed electron. And it's a little more harmful because it's so small and it's moving at a very high speed. It can go through our skin. Skin is not enough to block it, but we can block it, and we can block it with metal or wood. And you see alpha. Alpha is big and slow moving because it's big, and it can get blocked by paper or really just about anything. Beta, however, it's just an electron. It's very small and high speed electron though. It can easily go through paper because it's so small and fast, and it can go through skin, and it can get into our cells once it gets past our skin and do some damage. So if I had a beta emitter sitting right next to me right now, I would be worried. I wouldn't want to be sitting next to it because I know it could get into my cells and do damage. But I could wrap myself in some aluminum foil and might be okay then, right? Because metal will block it and water will slow it down and partially block it as well. And wood, we put wood. We didn't have a picture of wood, but we put wood down there too. Okay, now a beta emitter would be tritium, which is hydrogen-3. It's a heavier isotope of hydrogen, and it glows in the dark. So sometimes things that glow you want to be careful around because it might mean that they're radioactive. Not everything that glows, though, is radioactive. Then the third type of particle is a gamma ray. It's not really a particle. It's a ray. It's energy. It's pure energy. And so here's the Greek letter for gamma. It kind of looks like a Y. I would draw it by making like a Y with a loop in the tail. And then the symbol 0/0 because it is not a particle. It has no mass and no atomic number. And so it's 0/0. Now it is pretty harmful because it is high energy rays that can go through just about anything. We can really only partially block it by several meters of concrete or some lead, and that we show that right here in the picture. It can go through the concrete. It's going to slow it down, but we need it to be really, really thick, but the lead will block it. And that's why you wrap yourself in a lead vest when they take x-rays. High energy x-rays is what gamma rays are. Technetium is a gamma emitter. It's used in nuclear medicine, so it's one of the things when people undergo radiation therapy because they have cancer. That's one of the things they use. And here it talks about how we've never really found any technetium because it's so radioactive. It decays so quickly that we believe, anyway, it's just decayed away, and that's why we haven't found any. Beta, how we make a beta, like here's the particle, but it's a Greek letter called beta. Here's what the Greek letter looks like. It's like a B with a tail at the end of it, like that. And then alpha, here's our Greek letter alpha. Here's the particle version, but the Greek letter is that. That's alpha. All right, so now we're going to use those three types of particles to write what's a nuclear equation. So a nuclear equation is very similar to a chemical equation, except we're really focusing on changes in the nucleus. It still obeys the law of conservation of mass, which says the mass of the reactants will equal the mass of the products. And so here's a nuclear reaction that's undergoing alpha emission. The way I know it's alpha emission is because right here I have a particle after the arrow, which means it emitted it, and there's our alpha. So what I notice here is if I look at my top number, and remember your arrow is where the equal sign kind of fits in, and the reactant side has to equal the product side. So the numbers are what we're making be equal. 238 equals the top number here, 4. And you see the plus sign, just carry it on up, plus this next number, 234. Is that a true statement? Does 238 equal 4 plus 234? Yes, it does. So we have obeyed the law of conservation of mass. The mass of the reactant equals the mass of the product. The same thing on the bottom. Although the bottom number doesn't tell us the mass, it still has to be equal as well. So 92, and here's the equal sign again, equals 2, and then the plus is right there, plus 90. Is that true? Does 90 plus 2 equal 92? Yes, it does. So both the top and the bottom numbers have to be equal. Okay, and so what happens is uranium is really big. It's radioactive. So what it does to gain stability is it releases 2 protons and 2 neutrons, which is what helium is, and now it turns into thorium. It turns into a completely different element. Then the next one, 234 equals, because here's the arrow. Does 234 equal 0 plus 234? Yes, it does. Okay, then the same thing on the bottom. 90 has to equal, and now let's look closely at this one because that's a negative one, and you need the negative, plus 91, right? 91 plus negative 1 equals 90. Yes, it does. Okay, so everything obeys the law of conservation of matter. Now this one's beta emission because this right here is your beta particle. Okay, so thorium is radioactive, and when it decays, or when it tries to gain stability, what it wants to do is release this electron, this high-speed electron. So it turns a neutron into a proton and an electron. Okay, so the electron gets released, and so here's where that proton went, right? It went from 90 to 91. And so you just have to be able to do the math, though. It's really simple. Okay, so we're going to try some right here, and I'm going to switch screens. Okay, and then we're also going to tell whether it's alpha, beta, or gamma that's being emitted. So remember what we do. The top numbers have to be equal. So I'm doing 226. The arrow is the equals, and then 4, and then plus, and then this empty box is what I'm trying to figure out. Okay, now up here, we had already been told what it was. But let's pretend like we didn't know. Like this is our empty box, and this is what we're trying to figure out. So I know they have to be equal. So this I could just call x, right? So 226 equals 4 plus what? What is that x? Well, to solve for x, it's just 226 minus 4, which is 222. Okay, that's the top number. Then I do the same thing on the bottom. It's 88 equals 2 plus something. I don't know, x. So what is that x? What number plus 2 equals 88? No, that's 86. So now I have the top and the bottom number. So now I would get my periodic table because it's the bottom number, you remember, that tells me what the element is. Find 86, my atomic number 86 is right here. And so now I know that element is radon, Rn. So I'll put the symbol in now. And now I've completed that. The only other thing I need to do is tell what type of emission, alpha, beta, or gamma. And so I look after the arrow, right, and here's alpha, right? So this right here tells me this is alpha emission. It emitted an alpha particle. All right, let's try the next one over. So again, top numbers, 234. The arrow is where the equals sign goes. Equals, this is what I don't know, so I'm just going to call it x. And then bring down the plus sign, and then 234. So 234 equals x plus 234. So what is x, right? X is just 0. Okay, then I do the same thing for the bottom numbers. 90 equals something, x, plus 91. And so to solve for x, I would just subtract 91 from both sides. So it's 90 minus 91, which is negative 1, right? Or 91 minus 1 equals 90. Now you got to remember, what symbol is that? I'm not going to get my periodic table because there is no negative 1 up here, right? It's just a 1, right? So we have to know that that is our beta particle right up here. So what I need to put in there is an E. And I know, because now we talked about it, right? That is beta. So this one is beta emission. All right, let's do the next one. 204 equals 4 plus what? Or we can probably just do that and just write it in as 200, right? You don't always have to write it out. So 82 equals 2 plus what? Well, that would be 80, right? Because 80 plus 2 equals 82. All right, and then the bottom number, the 80, tells me what it is. So I find 80, here's 80, it's Hg, mercury. So then I put in the symbol, Hg. And then what type? Alpha, beta, gamma. Well, here is, so this is alpha emission. One more, we got 66 equals 0 plus what? Well, that would just be 66. All right, and I got 29 equals negative 1 plus what? Or something minus 1 equals 29. So that would have to be 30, right? 30 minus 1 equals 29. So what is 30? That's right here. It's zinc. So that's the symbol I put in. And then this one is, well, here's my particle, right? And that's beta. So this is beta emission or decay. Now these are level 2, and the reason why they're level 2 is because there's more than just one thing to start with, right? These all had 1 and they split into 2. Well, this has 2 and it splits into 2. Okay, but you still work it the same way. It's just a little harder with the math, but I still do the same thing. I'm going 100 plus 0 and then equals, that's where the arrow is, something plus 0. Well, that's got to be 100. Okay, then the bottom, 46 plus negative 1 equals something plus 0. So that's like 46 minus 1. That's 45 equals something plus, that would have to be 45, right? Okay, then we look to see what is element 45. That's RH, rhodium, so RH, okay? Now let's look at our particles. Well, we have beta and we have gamma. So it emits gamma, so that's emission. It's gamma emission. I wouldn't call it beta emission because beta was not emitted, right? It was bombarded with the particle, right? It was absorbed into it. Gamma is what it emitted. And then this one's a little harder too because now we got this 4 in front, and that's a neutron, right? A neutron N has a mass of 1 and 0 for its atomic number. It doesn't have an atomic number. And the 4 really means I have 4 of them. So it's really like writing that symbol 4 times, adding them up. So I got to remember that 4. So when I'm doing my math and I'm saying 249 plus something equals 263 plus, well, I got to remember there's 4 of them. So it's not 1 plus 1, it's plus 4 times 1. 1, 2, 3, 4. So it's plus 4. And then I got to do a little bit harder math now to solve for that x. 263 plus 4 is 267. And then that's 249 plus x, right? So I still got to solve for x. So I would subtract 249 from both sides. And so now that means x is 267 minus 249 is 18. Okay, so that's the top number, 18. And now I'll do the same for the bottom number. All right, and I may need more room somewhere, right? So I do 98 plus something equals 106 plus, and that's 0, 0, 0 plus 0 plus 0 plus 0 is still just 0, so plus 0. All right, so that's 98 plus x equals 106. And then I would subtract 98 from both sides. And so that means x equals 106 minus 98. 106 minus 98 is 8. So 8 is the bottom number. And the bottom number tells us what it is. So here it is, oxygen. Now, fusion and fission are also two types of reactions that happen in the nucleus. And so fusion is when two large nuclei, 2 or more, are split into smaller nuclei. And that's what happens in a nuclear reactor, a nuclear power plant. Here's that in picture form. So uranium's really big. That's why it's radioactive. It splits really easily because it's so big. And so a neutron will go and hit it, and that'll make it split in half, and it releases more neutrons along the way, and they hit more nuclei and make them split in half. But every time that nucleus splits, huge amounts of energy are released, and so are more neutrons. So in a nuclear reactor, you want fission to take place because you're trying to get that energy, but you want it to take place slowly to prevent a chain reaction, right? And so what we do is we add this moderator in here. It helps to slow the neutrons down, and that's how we make it go slowly. And that's one of the essential designs in a nuclear power plant to keep it from overheating and exploding. But we had that happen. We had that happen in Chernobyl, which is what you see here. This is the power plant before it exploded, and here's what it looked like when that chain reaction somehow got out of control and it exploded. And there's huge amounts of radiation got released into the air, and people still to this day can't really live there because it's still emitting radiation to this day, so much of it. And that was the worst nuclear disaster still to this day. We've come close, but we were able to learn from this mistake and keep other mistakes from getting out of control like this one did. And it's also what happens, fission happens in a nuclear bomb. This is a picture of a nuclear bomb during World War II when we decided to drop it on Japan to get them to surrender. And if you were standing really close to this, you were just incinerated, right? You turned to dust because of the huge amounts of energy. It just vaporizes you. And what happened too to some people, you kind of see the image here of the man standing next to the ladder. Well, when the bomb hit and he was in the path of that, the radiation was absorbed by his body, but it continued to go around him and hit the wall he was standing in front of. And so it makes sort of like a photographic image of him and his ladder. Of course, he died, but his image is forever burned into the side of that building. Okay, then the other type of nuclear reaction we can have is fusion, when smaller nuclei join to form a larger nucleus. And that is what happens in the sun. So hydrogen is the smallest of all the nuclei. The sun is just a big ball of hydrogen to start with, but it's really, really hot. So the hydrogen goes really, really fast, and when they collide, since they're going so fast, they stick together, and now you formed helium. So a hydrogen plus a hydrogen is no longer hydrogen. Right now it's helium because it's one proton, one proton. Now the two protons stick together, and now you've got an atomic number of 2 instead of 1, and that makes it helium. And huge amounts of energy are also released. Even more energy is released than a fission reaction. Okay, now radiation is not always a bad thing. We do use it for good, okay? And so here we use it to create power. This is a nuclear power plant, really, that's not very far from us, right down the road, kind of by a little past Galveston area. And it's where fission takes place. Beta and gamma is really good at killing things, including humans, but it can also kill bacteria. So we use it to sterilize things. It can also kill cancer cells. It's one of the few things. Gamma kills cancer cells. So we use it in radiation therapy to get rid of cancer. And like we've already talked about, alpha emitter is used in a smoke detector. Okay, so using what we just talked about, I would like for you to pause the video right now and try to fit these words into whether they relate to fusion or fission. All right, welcome back. Did you get your answers right? Here they are.